Hi, my name is Lexi, and I'll be presenting the story of light. So, a history to light is that in ancient Greece, Aristotle lived from 384 to 322 BC, and his famous quote for light is, "The essence of light is white light. Colors are made up of a mixture of lightness and darkness." And then Al-Hazzan, who lived from 965 to 1040, was a mathematician, astronomer, and philosopher in Islam. And his major quote was, "Why does the moon appear larger near the horizon than it does when higher up in the sky?" And he really focused on reflections, concave mirrors, and glass spheres. And he confirmed that light comes from objects. So these two men were really the foundation of the discovery of what light was, and they were just starting to figure out that light was something and that they should be studying it. Then Christian Huygens, he lived from 1629 to 1695, and he was a Dutch mathematician, and he established the wave theory. Then Sir Isaac Newton, who lived from 1643 to 1727, he quoted, "Light is comprised of colored particles." He greatly contributed to the science of optics, including lenses, prisms, mirrors, telescopes, and microscopes. He announced his theory of light and color in 1672, and he quoted, "Light is a mixture of various colors having different refractivity," and he thought of light as being a particle. So this was really the start of, is light a wave or is it a particle? So Thomas Young, who was born in 1773 and died in 1829, he discovered the diffraction phenomenon, and he conducted the double slit experiment. So after conducting his experiment, Thomas Young found some very interesting things. So what he was expecting to find was what was on the left, which was particles going through the two slits and then two sources of light um, on the screen. But what he found was diffraction, which is bending of light waves around an object, which can be seen on the picture on the right, which is the actual thing. So as you can see, the light is coming in on the left, it's passing through that slit, and then light is going through it, but it's diffracting. So it's bending into that small arch, and as it keeps going, the light keeps getting bigger and bigger and bigger, kind of like a ripple effect. And then, as you can see, when the light is passing through, the pattern on the right represents the bright spot in the middle is where the waves are the most concentrated. And then there's two dark places, and that's where the waves don't line up. But then there's another light spot, and that's where the waves line up again. So it just keeps happening like that. Line up, don't line up. It's kind of like the ebb and flow of light, and that's how he figured out that light is a wave. So to answer that question, is light a wave or is it a particle? It's kind of both and it's kind of neither. So on a normal scale, light is a wave, but on the quantum scale, light is a particle. So the quantum scale is a very, very small scale. It's down to atoms, very small quantum scale. And to explain that, in the 20th century, there's more research coming out, there's more studies being done, and researchers are finding that when light hits metal, atoms in the metal are absorbing the light, and it's leading us to question if light is a wave because it's acting more as a particle, and that creates quantum mechanics. So in reality, light is something in itself that's hard for our eyes to understand because it's such a weird concept that it's hard to explain it as a wave or a particle. But in our terms, it's easiest to explain it that way. So the basics of light. So as we know, light is measured in frequency, and frequency is the number of waves that pass through a fixed place in a unit of time. So the higher the frequency, the shorter the wavelength, and the lower the frequency, the longer the wavelength. So as we can see here, our visible light, red is a lower frequency where blue is a higher frequency, and all of the colors in between are a variation of different frequencies that we can see. So here is the electromagnetic scale, and we have 7 different wavelengths. So we can only see a small portion of these wavelengths, and why is that? Well, there are cones and rod-shaped cells in our eyes, and they can only register a specific frequency of wavelength. So all these gamma rays, X-rays, ultraviolet, infrared, microwave, and radio waves we can't see, but we can see that small portion of visible wavelengths. So as you can see here, I really like this diagram because it shows the true size of each wave. So gamma rays are super, super small. They're as small as atomic nuclei. And then radio waves get as big as buildings, or even bigger, as they're really big. And then all those waves in between show the different sizes that they can compare to. So now I'll go through all 7 different wavelengths more into detail. So first we start with gamma rays. They're the highest frequency of wavelength. They are emitted from an excited nucleus, and they're also the most harmful external hazard to humans because they can pass through bones and teeth and basically your entire body, and they can destroy living cells. They cause gene mutations and cancer, and they're formed by very high temperatures in space, but most of them are soaked up by the Earth's atmosphere, which is a good thing. So X radiation, or more commonly known as an X-ray, is just like what you'd see at a doctor's office. So what happens is a machine puts out a small amount of ionizing radiation, and then as the X-ray passes through your body, it is absorbed at different rates, just based on what it's going through. So if there's bone, it's not going to pass through, but if it's a soft tissue, then it'll pass through. And then an X-ray image is created by the rays colliding with the photographic metal plate underneath you. So on the right is a diagram of what's going on. So as you can see, the X-rays are being emitted from the machine, and that's why you see a lot of X-ray technicians getting out of the way so that they're not exposed to that radiation over and over again. Whereas if we're getting X-rays, it's usually not that often, so it's usually not that harmful for us. So as you can see, the X-rays are passing through the bone, and so where the bone is, that X-ray radiation is absorbed into your body, but the soft tissue or between your fingers, that type of thing, where it's all black, that's where the X-ray has hit that photographic metal plate, and it is absorbed into that plate instead of you, and that's how that picture is formed. And then the next level is ultraviolet radiation, or more commonly known as UV radiation. It's emitted by the sun and tanning beds. It produces vitamin D in the body, which is very important. And prolonged UV exposure may cause skin cancer. And to protect yourself, you should wear sunscreen, limit sun exposure during peak UV times, and wear sunglasses because it can also damage your eyes. So there's 3 different types of UV. There's UVA, B, and C, where UVA can hurt your eyes. UVB is where you get that skin cancer, and UVC is blocked by our atmosphere, so you don't get any of the UVC. Visible light is what we've been talking about this whole time. It's what you can see. It's your blues to reds. And I thought a cool thing about visible light is there's this thing called light splitting. It can be done using a prism, so you have white light or light from the sun going through a glass prism, and then what pops out is a continuous spectrum, basically a rainbow. So you might be thinking, how does a rainbow work? Well, when a light hits water particles in the atmosphere or the air, then this light splitting happens again, and a rainbow is formed from those water particles in the air. Now we're on the other side, where we get to a lower frequency, and we're on the infrared radiation. So this is where thermal imaging cameras come into play, and they detect thermal energy of an object, just like this teapot here. It also has to do with remote controls, optical fibers, and electric heaters. Microwaves. So this is like our daily microwave in our kitchen. So how does a microwave work? So the rays penetrate the food, and then that causes some molecules to vibrate, and then those molecules generate heat. And microwaves use a frequency of 2.45 gigahertz, and that means that the electric field switches from positive to negative 2.5 billion times per second. So that's super fast, and that's how it creates so much heat. But there can be metal, because metal heats up too fast and it causes a fire almost instantaneously. Then we have radio waves. So this is our largest wavelength, and its radio waves are produced by a transmitter. Different frequencies are sent out, and then it's kind of like in a Morse code type way of frequencies, and then it's detected by a receiver at the same frequency. So both the transmitter and the receiver have to be on the same frequency for them to be able to like communicate. And then this receiver decodes the message, and the message could be in sounds, images, or data. And then the uses of the radio waves can be in FM and AM radio, cell phones, the military uses them, Wi-Fi, Bluetooth, and more. So where does this apply? Everywhere. Like I said, it's in radios, microwaves, colors, x-rays, all those things I just mentioned. Some additional information is that people who are born with color blindness, this is caused normally by a genetic mutation that causes the cones in their eyes to develop incorrectly. So like I said earlier, we have cones and rods in our eyes that detect this light, but if you're colorblind, it's normally because these cones and rods are developed incorrectly, so they can't register those colors. And the picture on the right is actually a real life picture of a rod and a cone in somebody's eye, and this picture is taken by a microscope, which a microscope uses light to enhance an object, making it seem bigger by bending the light towards your eyes using a curved glass. So like I said, light is used everywhere. So in conclusion, there is a long history of light, and many people contribute to it just because it's such like a out of this world idea that you can't see a lot of it. So it's taken a lot of years to figure out, and we're still figuring it out. And then there are many different uses of different frequencies of light, and that's why I think it's so cool. Thank you for watching.